Right. Welcome you once again. And this is the last episode whereby we are going to determine we are going to explain or to describe the experiment that is used to determine the order of reaction with respect to iodine in the iodination of propanone catalyzed by sulfuric acid. It's a very common question and a very common analysis in the laboratory. So what we have to do here, we get fixed volumes. I outlined it first so that variety can be overcome. But what we do, we get fixed volumes of propanone and sulfuric acid, and we measure them into a conical flask. Then we also get a fixed volume of standard solution of iodine in potassium iodide. We also add it to the flask. So in the flask, it means that we have propanone, sulfuric acid, and iodine. Then the time at which the iodine is being added is noted. So you note the time at which it starts being added and the time it completes reaction. Now, after a few minutes, a sample of the reacting mixture is pipetted into the conical flask, and then you add a solution of sodium carbonate simply to stop reaction by reacting it, but because the sodium carbonate is going to neutralize the sulfuric acid. So that's why I'm saying that after a few minutes, a sample of reacting mix is pipetted into a conical flask in solution of sodium carbonate added to stop the reaction instantly by neutralizing the acid. Then the time at which the reaction stops is noted. You noted when you added the iodine, and you've noted when you've added when the reaction has stopped. Now, the resultant solution that has iodine is pipetted, right, and titrate against standard sodium thiosulfate solution in presence of starch indicator. And this one will give you the amount of iodine. How? You're going to get, since this is a standard solution, standard sodium thiosulfate, you're going to get the moles of standard sodium thiosulfate. That one can use the mole ratio to get the moles of iodine, and then you can get the amount of iodine. So you are going to repeat the procedure for some minutes to determine the average amount of iodine that has remained. And then the original iodine potassium iodide solution can also be pipetted and titrated against sodium thiosulfate in order to obtain the volume of sodium thiosulfate that reacts with it. Then the volume of sodium thiosulfate required can be plotted against the time taken since the start of the reaction, and is going to produce a straight line with a negative gradient, implying that it is zero order with respect to this. WRT is with respect to iodine. Here is the equation that shows this. So one can say, determine an experiment show that the order of reaction with respect to iodine, the iodination of propanone is zero. Or they can say, describe an experiment to determine order of reaction with respect to iodine in iodination of propanone catalyzed by sulfuric acid. So the procedure is as brief as this. So it's a matter of knowing how you get different amounts, all right? You begin by adding propanone, sulfuric acid, and iodine into the flask. Then after minutes of reacting, you pipette some mixture and you add sodium carbonate to neutralize, and then you record the time and after the reaction has stopped. Then you titrate the resultant that has iodine with thiosulfate so that you obtain the amount of iodine. That is done for some time so that you get an accurate value by taking the average. Then the original iodine in potassium iodide also is pipetted with the sodium thiosulfate so that you determine the volume of sodium thiosulfate that reacts with it. After which you plot a graph of volume of sodium thiosulfate and time that has elapsed. The graph will be a straight line, will produce a straight line with a negative gradient, showing that it is zero order with respect to iodine. I'm going to explain or to describe the final experiment. And that final or the last experiment, it is also a common one. Describe an experiment that can be carried out show that the catalytic decomposition of hydrogen peroxide is a first order reaction. Now here we are looking at decomposition of hydrogen peroxide to be a first order reaction, and for this case, what we do still, it's not too much. You just need to note what has to be done, basically the reagents that we involve here. Okay, so the first procedure, since we are looking at hydrogen peroxide as a major material, we can say a known fixed volume of hydrogen peroxide solution is pipetted. After pipetting a known fixed volume of hydrogen peroxide, we shall add sodium hydroxide solution. So sodium hydroxide solution is added to it, followed by iron 3 chloride solution and the stop clock started. Let me say started simultaneously at a go. Simultaneously. Here, our iron 3 chloride is going to work as a catalyst, okay? Then 3 is that the mixture, we shake the mixture. So the mixture is shaken. And I have to stand for 3 minutes. Then after that, we draw a known volume of the reaction mixture. Is drawn. Then excess sulfuric acid, that must be dilute, is added. Stop decomposition. Remember, what is decomposing is the hydrogen peroxide to form oxygen and water. Then we have to repeat that procedure. The procedure is repeated, maybe at intervals 3 minutes before you add sulfuric acid and a tighter value. V1 noted. Okay, so now it is after this that the initial concentration of hydrogen peroxide before decomposition is obtained by titrating the original hydrogen peroxide with the potassium manganate 7 or with potassium permanganate, and volume of potassium permanganate used, which I can call V naught, is noted or is recorded. So here, when we repeated the procedure, we can get volume T. So another step, I'm going to explain that we go. We shall plot a graph of logarithm of V naught out of VT against time is plotted, and a straight line is obtained. Before I go to the graphs, we really need to know what takes place here. We say that we pipette a known volume of hydrogen peroxide, then we add sodium hydroxide followed by the catalyst iron 3 chloride. As you do this, the reaction will start taking place, so you also start the stop clock. Then you'll shake the mixture and allow it to stand for 3 minutes. Then you draw a known volume. Okay. You draw a known volume of the reaction mixture, and then you add, from the mixture, you will add sulfuric acid so that you stop hydrogen peroxide from decomposing. You repeat the procedure for some minutes. Before you add sulfuric acid, first repeat it so that you get the volume at which full reaction takes place. Then the initial concentration of hydrogen peroxide used can be obtained by titrating the original with potassium permanganate, and that one will also give you the volume of potassium manganate used, which I have called V naught. Then you plot V naught over VT under its logarithm, then you plot it against the time taken. So that one will produce a straight line. And from the previous graphs we've seen, we saw that for this case, you can produce different graphs. So this is log V naught over VT, and this is T. Time is in seconds, logarithm has got no units. So this one, we say that the slope is equals to K out of 2.303. So you can easily determine the rate constant and get other variables required. So as someone who plots a graph of VT only against time, you get a graph of this nature. And someone who plots volume of V naught for potassium permanganate against time, volume of potassium permanganate, you're going to get a graph of this nature. But our main interest is this. So we shall take this graph, which when treated, we can get all the values intended to be obtained. So you need to be very careful, especially based on the types of graphs you are expected to really obtain. Okay. So someone who plots the one of volume of potassium permanganate V naught against time, that person is going to determine the half-lives, or is going to get the half-lives. Okay, and those half-lives will be found to be constant. So from the graph, one who has used this, one can say, one who has used the first one can say graph of log V naught over Vt against time is plotted, and a straight line is produced with a positive gradient, showing that it is a first order. But for this case of when we plotted the third one, the volume against time, you will say that a graph of volume of potassium permanganate against time is plotted. And from the graph, the half-lives are determined and are found to be constant, implying that the reaction is first order. So someone who has used this, you'll obtain, of course, being a curve, you're going to be obtaining half-lives, and they'll be found to be constant at all the levels. Being constant, it means that they have first order, the reaction is first order. Or you can use logarithm V naught over Vt against time, you produce straight line with positive gradient, and still conclude that the reaction is a first order reaction. I've got a guiding question. I've gotten a guiding question that we can enjoy here. Here is a guiding question that we can enjoy. It's very good. The volume of hydrogen peroxide solution was decomposed in presence of platinum. The amount of hydrogen peroxide after time t was found by withdrawing alcohol portions of solution. Then adding sulfuric acid, adding dilute sulfuric acid, and titrating with potassium permanganate. Solution. The volume of Vt of potassium permanganate solution were as follows. You have time in minutes. You have it in cubic centimeters. You have 0, 5, 10, 20, 25, 30, 35, 40, 45. Here, 12.30, 9.20, 6.90, 5.20, 3.90, 2.90, 2.20, 1.60, 1.20, 1.15. That is plot a graph of log VT against time. That is a B, state the order of reaction with respect to hydrogen peroxide. Give a reason. C, determine the rate constant for the reaction. D, calculate the half-life for the reaction. So that is it, and I really wish that we do the needful. I really wish that we do the needful, and then from here we shall be now looking at a new topic of phase equilibria, which I will record at the same time with ionic equilibria, where we're going to cover solubility equilibria and other related work. I wish you all the best. Thank you for watching. Tell a friend to tell a friend to subscribe to this channel for the instant flow of the academic content. Thank you so much.